The F-35's stealth was optimized for the radar that guides missiles. The radar that finds aircraft operates on entirely different wavelengths, and at those wavelengths the F-35's shaping stops working. The B-21 solves both problems simultaneously. The reason it can and the F-35 cannot is a physics problem. Coating cannot solve it. Only size can. The F-35's stealth was not designed to fail against VHF radar. It was designed to accept that failure as a calculated trade-off the mission could survive. Radar works by transmitting electromagnetic energy and measuring what returns. Stealth controls that return, redirecting energy away from the transmitter or converting it to heat before it reflects. Both mechanisms depend on frequency. A shaping solution optimized for a 3 cm wavelength can be geometrically irrelevant at a wavelength 30 times longer. That gap is a physics constraint, not a design flaw. The radar that guides a weapon to its target, X-band fire control radar, operates at approximately 3 cm wavelength. That is the frequency the F-35 was built to defeat. At 3 cm, shaping works because the wavelength is far shorter than any feature on the aircraft's surface. A wave that's short striking an angled panel reflects away from the source at a predictable angle, like light off a tilted mirror. The energy that returns to the source radar drops to a fraction of what an unshaped aircraft would produce. Against X-band fire control radar, the F-35's geometry performs as designed. The VHF surveillance radar operates at 1 to 2 meters wavelength, roughly the height of a standard interior door. At that scale, the physics changes entirely. When a radar wavelength approaches the physical dimensions of a feature, it is illuminating. The F-35's wing leading edge, its inlet lip, its canopy rail, that feature stops redirecting the wave. It resonates. The electromagnetic energy couples into the structure and re-radiates outward in all directions, including directly back toward the source. The F-35's shaping that defeats X-band fire control radar provides almost no cross-section reduction at VHF. Against VHF surveillance radar, the aircraft appears with a cross-section approaching its physical size. Radar-absorbent material cannot close this gap. The RAM on the F-35's skin is tuned to absorb X-band energy, a layer approximately 1 to 2 millimeters thick, close to the thickness of a credit card, matched to the 3 centimeter wavelength. Effective absorption requires material depth proportional to the target wavelength. A RAM layer tuned to absorb 1 meter VHF energy would need to be approximately 25 centimeters thick. No aircraft skin can carry that thickness and remain aerodynamically viable. Optimize the shaping geometry for X-band, and the leading edge radius stays sharp enough for transonic aerodynamics, but too sharp to avoid resonance at VHF wavelengths, where the edge dimensions fall directly in the coupling regime. Optimized for VHF, and the leading edge radius must increase to a size that creates unacceptable drag at the speeds a combat aircraft requires to survive. C. A fighter-sized airframe cannot satisfy both constraints simultaneously. The trade-off was accepted deliberately. The F-35's stealth requirements prioritized X-band performance because X-band fire control radar is what guides weapons to aircraft. The logic was sound. VHF surveillance radar can find the F-35 at long range, but detection without a fire control solution does not produce a kill. The VHF system locates. The X-band system kills. Defeat the X-band system and the VHF detection becomes tactically irrelevant. The adversary knows a contact is out there but cannot guide a weapon to it. That logic held until adversary integrated air defense systems developed fire control solutions derived from VHF tracking data without requiring an independent X-band lock to close the kill chain. But the F-35's designers knew this. The frequency trade-off was in the requirements document. The question was never whether VHF radar could find the F-35. It was whether finding it was the same as killing it. The answer changed, not because the F-35's shaping degraded, but because the threat architecture evolved. An adversary who can derive a targeting solution from VHF data alone no longer needs the X-band lock. The F-35 was designed to deny. The kill chain closes through a different path than the one the F-35 was built to sever. The B-21 addresses this at the geometry level, not the coating level. A pure flying wing with no vertical surfaces removes the largest resonant structures from the aircraft's exterior. The F-35's tail fins, canopy rail, and inlet lip are near-resonant features at VHF wavelengths. Their physical dimensions fall close enough to 1 meter that resonance effects dominate their radar behavior, regardless of how they are shaped or what coating covers them. The B-21 carries none of those features. No tail fins, no canopy rail discontinuity, no inlet face visible from the forward threat sector. The structures that make the F-35 visible to VHF radar do not exist on the B-21's outer surface. The wave arrives. 1 meter of electromagnetic energy traveling at the speed of light meets a curved surface with no features at its own scale. Nothing resonates. The leading edge curves away. Energy diffracts forward into airspace the transmitter never monitors. The return that should travel back does not form. The geometry solved the problem the coating never could. The B-21's leading edge radius is large enough to stay outside the VHF resonance regime. Tens of centimeters, rather than the sharp edge geometry a transonic fighter requires. That radius is possible only because the wing chord behind it is long enough to carry it without aerodynamic penalty. Size is not a consequence of the B-21's design. It is the mechanism. Removing the tail fins eliminates the largest resonant features on the aircraft. But the inlet is still there, and the inlet is a bigger problem than any tail fin ever was. A jet engine's compressor face, the rotating fan visible at the back of a straight inlet duct, acts as a retroreflector. Radar energy that enters the inlet travels down a straight path, strikes the compressor face at near normal incidence, and returns almost entirely back toward the source. The gain from a compressor face retroreflector can dominate an aircraft's total radar cross-section, regardless of how well the rest of the airframe is shaped. An aircraft that has eliminated every other radar return source but left the inlet unaddressed is still visible. The inlet is not a secondary problem, it is the primary one. The B-21's inlet ducts are buried inside the wing structure and routed along a serpentine path, a continuously curving duct that changes direction multiple times between the inlet face and the engine. No radar wave entering the inlet travels a straight line. The duct walls are lined with absorbing material, and each curve redirects the wave's energy into those walls rather than forward toward the engine face. A wave that survives the first curve encounters the second at an angle that scatters it further. By the time any residual energy reaches the compressor face, it has attenuated through multiple reflections and absorption cycles to a level that contributes negligibly to the aircraft's total return. The inlet that would otherwise dominate the radar cross-section becomes acoustically and electromagnetically blind from the front quarter. The duct itself is long enough that straightening it would require an aircraft section roughly the length of a full-size sedan. That length is available inside the B-21's wing root because the wing is large enough to contain it. A fighter-sized airframe cannot route an inlet duct of this geometry within its fuselage cross-section without compromising either the duct's absorbing path length or the structural volume available for fuel and systems. The buried serpentine inlet is a solution that requires space. Space requires size. The B-21 is not harder to detect than the F-35 at the same frequencies. It is undetectable at frequencies where the F-35 was never designed to compete. Surface continuity extends the geometry solution to the aircraft's full outer mold line. In cruise configuration, the B-21 presents an exterior with no visible panel gaps, no protruding sensor housings, no antenna fairings, no navigation light fixtures breaking the surface. Weapons bay doors sit flush with the lower surface with edge treatments that maintain the electrical continuity of the skin across the seam. Communications antennas are embedded beneath frequency-selective surface panels that are transparent to the intended signal and absorbing at radar frequencies. Every aperture that would create a radar return on a conventional aircraft has been either eliminated or integrated into the surface in a way that controls its electromagnetic behavior. The outer mold line tolerances reflect how much the threat environment has evolved since the B-2 was designed. A panel gap of 3 mm on the B-2 creates a detectable return at X-band frequencies. The gap acts as a slot antenna, re-radiating energy at wavelengths proportional to its dimensions. The B-21's tolerance specifications are tighter because the threat set now includes higher frequency fire control systems that the B-2 was not required to defeat. A gap that was acceptable in 1989 is a vulnerability in the current threat environment. The manufacturing precision required to hold the B-21's tolerances across a full-scale bomber airframe drove changes to the production tooling that have no precedent in previous aircraft programs. Leading edge radius sizing sits at the intersection of every constraint the B-21 has to satisfy simultaneously. Too small and the edge falls into the VHF resonance regime. The feature couples with the long wavelength surveillance radar and scatters in all directions. Too large and the aerodynamic drag penalty at cruise altitude and speed reduces range below the mission requirement. The B-21's leading edge radius is measured in tens of centimeters, closer to the diameter of a tennis ball than to the sharp edge on a tactical aircraft, and that radius is carried across the full leading edge span without interruption. Satisfying it requires a wing chord measured in meters. The chord is available because the aircraft is large. The stealth requirement and the size requirement are the same requirement expressed in different units. A maintenance technician moves along the B-21's leading edge with a gloved hand. The surface offers nothing. No seam where one panel meets the next, no texture change where the edge treatment ends and the upper skin begins, no step between materials of different thickness. The cord runs from the leading edge back into the wing without interruption. The hand finds no transition because there is no transition to find. The outer skin is not a composite structure with RAM applied to its surface. The absorbing properties are built into the composite layup at the material level, engineered into the fiber orientation, and the resin system and the embedded conductive elements during the manufacturing process rather than added as a separate coating layer afterward. A coating can chip at a panel edge, delaminate from thermal cycling, absorb moisture through a surface scratch. A structural material with absorbing properties built into its composition does not delaminate because there is no interface between the absorber and the structure. They are the same material. The B-2's RAM required climate-controlled hangars and temperature-controlled repairs because the coating and the structure beneath it had different thermal expansion coefficients, stress that accumulated at the interface with every flight cycle. The B-21's outer skin does not have that interface. The maintenance burden that made the B-2 operationally dependent on its home base is designed out at the material level. The B-21 is described as the most advanced bomber ever built. That framing misses the point entirely. The RAM formulation is not optimized for a single frequency band. Earlier stealth aircraft used materials tuned to perform best at the specific radar frequencies in the primary threat environment, accepting higher reflectivity at adjacent frequencies on the assumption that those frequencies would not be used for fire control. That assumption no longer holds. Modern integrated air defense systems are frequency agile. They can sweep across bands, identify the frequency at which a target's return is highest, and dwell there. A material stack optimized for one narrow band presents a detectable return to any system capable of stepping outside that band. The B-21's material stack is specified to maintain absorption across a broader frequency range than any previous operational aircraft skin. The additional bandwidth costs weight. Each additional frequency decade of effective absorption requires material layers with different electrical properties, and those layers add thickness and density to the skin. The trade-off is accepted because the alternative, a material stack with gaps in its absorption curve, is a vulnerability a sophisticated adversary will find and exploit. The leading edge's internal structure handles the energy the outer geometry cannot redirect. Behind the shaped outer face of the leading edge, structured absorber layers are built into the internal composite stack. A radar wave at VHF wavelengths diffracts around the leading edge geometry rather than reflecting cleanly from it. Some energy bends around the edge and continues into the upper or lower surface rather than scattering back toward the source. The internal absorber layers intercept this diffracted energy before it reaches a reflective internal structure and re-radiates outward. The leading edge is not a passive geometric feature. It is an active, absorbing structure whose outer shape and inner material work together as a single electromagnetic component. The B-21 and the F-35 are not competing answers to the same question. They are sequential answers to two different questions that happen to share a target area. And the hardest part of the stealth solution is not the shape and not the surface. It is keeping the aircraft electromagnetically silent when the mission requires it to transmit. An aircraft that presents a minimal radar cross-section to every threat radar in the area can still be located by any passive receiver within range if it is transmitting on communications, navigation, or sensor frequencies. Passive detection requires no transmission from the detecting system. It only requires that the target emits something. A B-21 with a geometrically and materially perfect stealth solution that keys its radio at the wrong moment is detectable by any system with a receiver tuned to that frequency, at ranges that can far exceed the protection radius of the stealth geometry itself. The B-21's own sensors use low probability of intercept waveforms, spread spectrum emissions at power levels close to a household Wi-Fi router's output, distributed across wide frequency bands in patterns designed to be statistically indistinguishable from background noise to a receiver that does not know the specific waveform being used. A conventional radar emits a coherent pulse that any receiver can detect and locate by its power and frequency. The B-21's radar emits something that looks like noise floor elevation, unless the receiver has the waveform key. The aircraft can illuminate a target and receive the return without announcing its position to passive detection systems operating in the same airspace. Off-board targeting extends this further. The B-21 is designed to receive GPS coordinates via low probability of intercept data link from satellites, other aircraft or ground stations, and release weapons without activating its own targeting radar at all. The weapon flies its own terminal phase using its onboard seeker. The B-21 transmits nothing during the weapon's release sequence. An adversary monitoring the electromagnetic environment in the target area detects no emission that indicates the B-21's presence. And then the weapon arrives. The weapon's bay doors open for the minimum duration the ejection sequence requires, a duration closer to a camera shutter than to a deliberate door cycle. Every millisecond the door is open adds to the radar cross-section integration time available to a threat system scanning the area. The B-21's ejector system is optimized to minimize that window. The RCS spike from an open weapons bay is the largest single radar return the aircraft produces during a mission, and the door management protocol treats it as a vulnerability to be minimized rather than an operational necessity to be accepted. The emissions control plan for a B-21 sortie is briefed in the mission planning cell the night before. Every frequency the aircraft might transmit is listed. Approved transmissions, prohibited transmissions, the time windows during which each is permitted, the consequence of a single unplanned emission at the wrong moment in the ingress profile. And the crew internalizes it the same way they internalize fuel states and threat envelopes, not as a checklist item to be completed, but as a constraint that shapes every decision from engine start to weapon release. Stealth is not a property of the aircraft in the hangar. It is a discipline practiced by the crew from the moment the aircraft leaves the ground. The radar that found the F-35 was always going to find the F-35. The engineers who designed the F-35 knew it, built the best aircraft the physics and the budget allowed, and accepted the trade-off because the mission could survive it. The B-21 is the answer to the question they knew was coming. Built large enough to solve a physics problem that no smaller aircraft can solve, quiet enough to defeat a threat architecture that no previous bomber was designed to face, and disciplined enough in its emissions to remain invisible in an electromagnetic environment that every previous stealth aircraft eventually illuminated. The size is the solution. The silence is the weapon. The shape makes both possible.